Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today we'll be talking about concentration of solutions, and we'll be talking about the effect of volume of solvent on concentration, the effect of number of particles on concentration, how do we prepare solutions of known concentrations, and how do we calculate the molar concentration of solutions. In the medical field, knowledge of the concentrations of dissolved substances in body fluids is essential. Any drastic deviation in concentrations of these dissolved solutes could be detrimental to patients. Diagnosis of various diseases can be made by studying changes in concentration of various substances in blood and urine samples. Elevated blood glucose levels, for example, is indicative of diabetes mellitus, and high levels of creatinine in someone's blood and urine is indicative of kidney failure. The concentration of chlorine in your drinking water must be high enough to destroy all the pathogens present, but low enough to avoid any side effects to users. Every day, millions of people who are too sick to eat or drink are fed intravenously with saline solutions. To reduce the risk of complications and death, technicians must ensure that the concentrations of all dissolved nutrients in saline are compatible with blood plasma. Too high a concentration of sodium in the blood, for example, can cause the heart to stop. Other substances given to patients must be subject to the same type of scrutiny. Doses of medicines administered to patients must be well calculated depending on the weight of the patient so that their concentrations in blood remains within acceptable safe limits. An excess of blood thinner, for example, can cause severe hemorrhage. Solution concentrations have wide-ranging applications, such as in analytical chemistry, nutritional studies, cooking, soil agronomy, pharmacology, and environmental science, among others. This chapter teaches how concentrations of solutions are calculated and how solutions of required concentrations are prepared. Calculations of the concentration of ions from the dissociation of ionic compounds are also taught. We'll look at how the volume of water in a solution affects its concentration. So here we're given two different scenarios where you're given two containers with the same volume of water. But in this first one here, you can see we're dissolving 16 particles of a particular solute, and in this one here, you're having 8 particles in the same volume. It's analogous to like you have a cup of tea and someone put 2 teaspoonfuls of sugar and there's only 1 teaspoonful. You will notice if you taste your tea, which one you think will taste sweeter. Definitely this one is sweeter because of the higher number of sugar particles there than this one here. So what we say in this case is that the concentration of this solution A will be higher than the concentration of solution B. And that, of course, is attributed to the larger number of particles here than in that one there. So the conclusion that we'll make is that the concentration C, we'll use C to represent concentration, and the number of particles is related to this number of moles. So there's a direct relationship between the concentration of a solution and the number of moles of particles that are dissolved in a certain volume of solution. We have a different scenario now, where we're having the same number of particles, or 12 particles in this solution here. And in this one here, we have the same 12 particles, but half the volume. It's like you're having some salt water, and somebody left that in the stove with the heat on, and it came down to that there. What do you think if you tasted this before, and then you tasted it afterwards? How do you think it'll taste? Obviously, when you taste it before, it will not taste as salty as when after you dried it down, right? What does volume have to do with the concentrate? When the volume is larger here, then in that case here, we saw that the concentration was less than when it was like that. So the relationship will be what? What can you say? Is there a direct relationship between concentration and volume, or inverse? Here is a concentration here. Your taste is very salty, so you can say the concentration is high. And we add water to that. If you put the same number of particles in different volumes, you find that the concentration will be different in both cases. So I'm asking the question now, what relationship exists between the concentration of a solution as you change its volume? Is it direct relationship or indirect relationship? You can see as the volume increases here, the concentration decreases. So there's an inverse relationship. So we say now that concentration is inversely related to the volume, and here volume is in liters. You measure volume in liters. So when you do concentration problems and volumes are given in milliliters, you'll have to change that to liters. So based on those two equations here, where we say concentration is directly proportional to the number of moles of particles, okay, this equation here and the other equation here, we can combine these two equations and we get this one here. It says that concentration is equal to the number of moles of particles divided by the volume they record. So this is what you have to memorize, this formula here, all right? So C is the concentration, it will be moles per liter, N is the number of moles, and V is the volume in liters. So knowing this formula here, we're now going to see how to calculate the concentrations of three different solutions here. All right. So here we are having, in this container A, 1 liter of solution, and that's 1,000 milliliter of solution, 1 liter here, and a half a liter here. We are having here 40 grams of sodium hydroxide, and if we divide that by the molar mass of sodium hydroxide, which is 40 grams per mole, you get 1 mole of that. So number of moles is 1 here, okay? So 1 mole of sodium hydroxide dissolved in 1 liter here. Over here, we're having 20 grams of sodium hydroxide, which is equal to 0.500 moles. Okay, so N is equal to 0.500 moles. In this case, we have the same 20 grams, and when you do the calculation, it also turns out to be 0.5 moles of sodium hydroxide inside here. Anybody wants to make a hypothesis with regards to how these concentrations can be compared to each other? What will be this one compared with that one there? How do you compare this one with that one without doing the calculation based on your intuition there? And how this one perhaps relates to that one there? You can think about it, make your hypothesis, do the calculations, pause the video and see how you get that. Here are our calculations. So what we do, C is equal to N over V. Number of moles in this case is 1 mole, and that is liters. We get this concentration here, That's half a mole, that one there, and you get the same concentration here. See? So solution A will be twice as concentrated as solution B. But because you're using less water in this case here than in this case here, definitely this one will be dilute compared to that one there. And that is why when you compare those two here, this has a concentration less than this one here. But look, these have the same concentration here. Why? Because you're using twice the volume with 1 mole, okay? And here you're only using half of that with half a mole, right? And therefore, the concentration of the particles inside here will be the same as that there. So that is how you go about finding the concentration of solutions. If you're given a mass, you change that to moles. If you're given the volume in milliliters, you change it to liters, and then you do your calculation there. All right. One of the misconceptions that students have is this, that if you take out a sample from this solution here, its concentration will change. So you want to use this calculation here to clarify that misconception. So what we'll do is this. We will take 100 milliliter sample of solution A. We take 100 from sample B and 100 milliliters solution from sample C. Then we'll try to figure out what is the concentration in each one of these here. We started off with 1,000 milliliters here. We have 1,000 milliliters here. But here we have 500 milliliters, okay? Because you're only taking 100 milliliters, it means the amount of solute you're taking will be 10 times less. Except in solution C, where it will be 5 times less, since the volume of the solution is 500 milliliters. This is the amount that dissolves in 1,000 milliliters, right? But now I want to know how much will be in 100 milliliters. So you take 1/10 of that, is like putting 100 over 1,000. So you end up with 4 grams inside it. That's the mass you're going to get. So the mass now of sodium hydroxide in this sample will be equal to 20 grams that we use, right? And 1/10 of it, which is this ratio here, okay? And that gives you 2 grams. Here now, you're going to take 20 grams, but you have 500 milliliters. You see that? 1/5. So you put 100 over that. This is your ratio of 100 over 500, and you end up with that mass of sodium hydroxide. We want to find the concentration. We know the masses. You have to change these now to moles, okay? So in every case, you divide by the molar mass of sodium hydroxide, which is 40 grams per mole, and you end up with that number of moles of sodium hydroxide in that one there, and that one there. Then you divide by the respective volumes. You take in that volume there, that volume there, and that volume, and that will translate into 0.10 liters, because you have to divide now. So that's what we did here, sorry. So this is it. That, and these here are the volumes, okay? This is the volume into liters, 0.1. Now you do this, C is equal to N over V. So the number of moles here is that, divided by that volume there. That number of moles is this, okay? And that number of moles is this. When you do your division, look, you end up the same concentration that we calculated originally, right? Originally, you get 1 mole per liter for A, solution A, 0.5 mole per liter, and 1 mole per liter in this case. So that's a misconception we try to clear up, that if you have a stock solution and even pour out a small quantity from it, the concentration of the small quantity is exactly the same that you got from the stock solution. Okay. Well, the concentrations are all the same, but look, the mass inside each is different though. Look, That was the mass there, 0.01, 0.100 mole. So the masses are different, but the concentration stays the same. So you see, look, that's the mass in that 100 milliliters. That mass is there, and that mass is there in these volumes here. I'm giving you to practice these ones, and these can be found in the solution manual. Answers to these also repeat there. So the next thing we'll do is an activity where we'll be making 3 sets of sugar solutions by dissolving 3 masses of sucrose in 3 different volumes of water. Before doing this activity, you'll be asked to make hypotheses about the relative concentrations of each solution. Okay? Having done the activity, you'll be asked to make calculations of the concentrations of the 3 solutions to test your hypothesis. So we'll go ahead and do this activity now in the next video.